So for this one right here, guys, for 43, a jet of water squirts out horizontally from a hole near the bottom of the tank shown in the figure. If the hole has a diameter of this much, what is the height h of the water in the tank? So how does that happen? How's that all going to play out? So for 43, you guys, they're giving you some data. They're saying it's close to, you know, it's elevated right here. It's coming out, so they're saying it's close to the bottom. So how close to the bottom I'm talking about? That's another indication in its own right. Close enough to the bottom that it is at the bottom, let's say. It's at a height of 1 meter, and it goes 0.6 meters outward. So you're talking about how high is the water in there that's contributing to this whole thing. The water's here. It's going to come out here, guys. It went to 0.6. This is 1 meter in height from here. They want to know how high the water is. The gut feeling is the higher the water, the more water that's in here. The more water that's in there, you guys, the more explosive the water's going to be coming out. So let's take a look at it. We're saying a bunch of things happen here that would make this happen. It's coming out from the side. It's coming out from the side, guys. The horizontal is going to tell us a lot. So they're saying you're going to fall 1 meter. And that's this right here. H Christian, is that visible? My bandage here is kind of hitting it, but is it coming out okay? It's okay. It's legible and stuff. Okay. Up close, I can see it's a little. It's kind of doing something to it. But let's look at this right here. Let's see how long this thing took to get to where it got. I want to see how long it took to fall. You know. Well, we got the h. We know what the height is. The height h is 1 meter. If the height h is 1 meter. Let's see what we can do here. Let's do some mathematics. Let's solve for t. And t is going to be, if you grind all of that out. So take this, solve for t. Do the mathematics that we can do. So let's do it. Get it to here. Plug in the 2 right here, the 9.8 right here, the 1 right here, the 2 right here, the 9.8 right there. So 2 times 1 over 9.8 squared with that quantity. That is going on like this. 0.4518 seconds. That is the flight time. Yeah, well, during that flight time, guys, the horizontal, it shot out at Vx. It shot out at Vx, and that's equal to the distance that it went, divided by t. What are we talking about? What we're talking about is 0.6 0.6 meters divided by 0.4518 seconds. We got 1.33 meters per second. Christiana's visible, right? Real well? Okay, very good. It's smudging every time I hit it with my finger here. But it's good enough. You guys are seeing it. Okay. So we got this right here. Vx is this. That's how it fires out. So that's at the at the very top. So there's a number of ways you can do this using Bernoulli's equation. You could say, okay, well, let's take a look at what's going on at the very top and what's going on at the bottom. Now, this is the weirdest thing, guys. There is atmospheric pressure at the top of the tank. The atmosphere is pushing down. The atmosphere is also pushing into the opening at the bottom of the tank. The atmosphere is pushing into the bottom of the tank. The atmosphere is pushing into the opening at the bottom of the tank, and the atmosphere is pushing in at the top also. So they balance out. So the pressure here, P1 on top and P2 on the bottom are one atmosphere of pressure. So they're equal to each other. They're equal to each other. I'm going to use, at the very top, the water's not going that fast. So I'm going to call that V1. Tell you what, let me write down Bernoulli's equation and kind of attack. Now there's a number of ways you can hit this problem. P1 plus rho g y1 okay. Well, we already just said the pressure at the top is one atmosphere, the pressure at the bottom is one atmosphere. That's why I'm doing that. We said that at the top, it ain't going that fast. The water ain't moving that fast. It's kind of moving at 0. At the bottom, it's definitely moving. This guy at the top does have a height. The height happens to be h. This guy happens to be h for the height. Here at the bottom, it's 0. Because the potential energy is 0. Remember, all of this came out. These rows are not the same as P. I know the P and the rho look a lot alike, guys. Just be cognizant of that. Look at the book as well. But there you go. We got this. We got rho g y1 equals 1/2 rho g y1 equals 1/2 rho v2 squared. What do you say? What do you say you divide by rho g on each side? That looks a lot like, well, y1 is the height h. v2 squared, the velocity as it comes out. That looks awfully familiar, guys. We saw that before when we were solving using the kinematic equations. So it comes out in a pretty interesting fashion. It's very familiar. I said that in the work as well. Plug everything in. Down here, this V2 is equal to Vx. The V2 is equal to Vx, the Vx that we got. Take the 1.33, square it, and divide it by the product, 2g. At the end of the day, that is 0.09025 meters. .09025 meters, or about 9 centimeters. That's 43. Christian, is this legible? You see it okay? All right. I may have to do something else, guys, to get us through this. All of this is in my notes. Look over, if you pan over to it, Christian, real quick. All of this you have fully solved for you. I might just give some kind of discussion pertaining to each one, and then you can read the rest on it, maybe when I do it. Maybe there'd be something along those lines. To do. Let me just see. Let me see what I can do. 88. All right, guys. 88 is a its own interesting matter. '88, they're saying there's a U-tube open at both ends. It's partially filled with water. It is then poured in the right arm and forms a column. L equals 5 centimeters high. Determine the difference H in heights of the two liquid surfaces. The right arm is then shielded away from any air motion while air is blown across the top of the left arm until the surfaces of the two liquids are at the same height. So, interesting. Determine the speed of the air being blown across the left arm. Assume the density of air is 1.29 kilograms per cubic meter. You wouldn't think air was that dense, but it is. All right. The basic look here, guys, for the U-tube open at both ends, partially filled with water and oil, and then poured in the right arm that forms a column that high. The look they got, the book's got a much better look at it than I can give you. Let me just walk through some of what you're going to have to do here. The weight on one side and the weight on the other side is going to have to be equal. So when you're doing the way they have it set up there, see exactly what we want to say regarding this. There's water, there's oil. Okay, let me see exactly what I want to say here, man. To walk through, I don't want to walk through it just for the sake of walking through it. I want you to kind of get it, but it's not. This is where I need you guys with me. We can talk about it a bit. All right, let's go. A U-tube open at both ends is partially filled with water. Oil is then poured into the right arm and forms oil is then poured into the right arm and forms a column L high. Determine the difference in the heights of the two liquid surfaces. The right arm is then shielded from any air motion while air is blown across the top of the other one until the surfaces of the two liquids are at the same height. Determine the speed of the air being blown across. Okay, shouldn't be too bad. It's still not going to be that easy to look at. Weight equals weight, you guys. I guess you could say there's water, and then somebody put oil in there, but they had to put a lot of oil in there for there to be some kind of a disparity. And some disparity did indeed happen. So there's two scenarios that kind of were brought forth here. So let me see exactly how we want to do it. Let's not worry a whole lot about how the tube looks exactly, but let's just say this much. If it's open at both ends, and the same cross-sectional area, that's water. That's water. Then they put oil. Okay, so this is oil. So this is water. And there is a difference in height of H. That's L. That's all water right here. That's all oil rather. That's L. And there's the H for the difference. And then down the road, they're gonna have wind go by, only one side. The other side is shielded. And that's gonna pressure everything up and bring everything to a place here. So the oil would be here. So they're asking a bunch of questions. There's different scenarios here, I guess you could say. There's an A, B, and a C, I guess. So well, the greater the speed of what's going on above it, it's going to tend to raise, it's going to lower the pressure. If there's wind blowing over one part, but not over the other, and the other's covered, you're not going to let wind blow over that. But over here it will. That happening will raise this thing up. This guy will get lower, whatever, it'll be less, there'll still be more pressure here, less pressure here, and somehow this is all going to balance out, depending on the speed of what's going on there. So, well, look at what they got, and I'll just say, with all of these scenarios, guys, for the A scenario, for example, determine the difference in heights of the two liquid surfaces. For that'd be, we're looking at B. For B, what's going on there. So, rule of air is this, rule of oil is this. Look, however this plays out, you guys, they're dealing with the B right here. On this side of the column, whatever weight is here is equal to the weight on this side of the column. Weight equals weight. I mean, this guy's coming down here. You could maybe make this a little better to look at or something. But if you're going to cut it right here, whatever weight is coming this way and whatever weight is coming that way, they're equal. Weight equals weight. So on side one over to the left and side one over to the left and side one over to the left and side two over to the right, weight equals weight. So to look at it, weight one equals weight two. What does that mean? Well, that implies that pressure equals pressure. Weight one divided by area, force divided by area is pressure. What does that mean? That means the row of the water times G times the grand total height times the volume. What's the volume? Cross-sectional area times height of the first guy. He ain't that high. And the other height of the second guy. You got to remember the difference between the two. You know, this is H1. This is H2. That's H2. And small h is H1 minus H2. We'll say from here to here. I mean, whatever, we'll just kind of approximate that this somehow goes straight or whatever. But, you know, H2, H1, and the difference between the two is going to be the small h. Rho WG AH1 over A equals all the other stuff going on, which is rho of water G AH2, that's where the water is, it's AH2. Plus rho oil got that. What's going on here? Well, isn't this, don't worry about the G. Isn't area times height volume? Volume times density is mass. Mass times G is weight. Weight divided by A is pressure. That's equal to the same phenomenon here. The water density times the volume times G, mass, the weight of the water, the weight of the oil, add it together, divide by A. Weight equals weight. Look at the difference. This is H2. This is H2. This is H1. Forgive me, I think we gotta look at it a little differently here, guys. H is gonna be a little different dynamic than that. It's gonna be a little different dynamic than that, guys. I'm sorry about that. Don't strike that if you could, the H1, H2. I didn't have that in my, I was wondering why I did not have it in my notes, and now it just kind of struck me why I did not have that in my notes. We got it. So, anyway, ride this thing along, you guys. Do all the mathematics that you got to do with this. And basically, how do you get out? How do you get out of the woods here? Multiply by A on each side. Multiply by A on each side, and you got RWG. Well, hold on here. There's A everywhere. Why do I even have to multiply by A on each side, guys? To be honest with you. A goes into here, A goes into each one of those A's right here. So what are we even worried about? I mean, we got this right here, G, H1, rho W, GH2, plus rho O, GL. Keep working this thing, guys. And you end up getting, if you do this, let's try to solve for H2 minus H1. It's not an easy thing to do, but it's not necessarily a hard thing to do either. Or H1 minus H2. Remember now, H1 is not as high. H2 is there, so let's see exactly how we'd actually done this, man. We might have, the oil is H2, that's not an issue. No, that's not an issue at all. All right, if you do this, subtract this quantity on each side, you get H1 minus H2 H1 minus H2 times the quantity rho WG equals rho 0 GL. Divide by, I don't know, do a whole bunch of things here, I guess, that you can do it at some point. Why don't you divide by rho WG on each side? We got this. If you actually, you know what? This guy right here is delta H. Delta H is H1 minus H2. This is 750 kilograms per cubic meters. This is 1,000 kilograms per cubic meters. The L right here was given to us as, I think it was just 5. It got cut off here when I was doing this, but 5 centimeters. So what do we got here for a DH? Plug in all appropriate values, you guys. Come over to here. So what's going on here? From the observation of the figure in the book, you guys, you can kind of say that the L itself, here's where it gets interesting, I guess you'd say. This is L right here. So what do you want to do here? Well, if this is H, and this right here is delta H, capital L is delta H plus small h. So if that's the case, it's a done deal. I mean, you could say H is equal to L minus delta H. H is H, L is 5, delta H is 3.75, H is 1.25, H is 1.25 centimeters for A. So, kind of an interesting move on that part. I mean, we could say that let's see exactly how they did this, how they want me to do it. Okay, so for B, that's kind of neat. That's kind of neat how that works out. So the thing is, we're looking at, and they're asking, I guess the question they're asking here is determine the speed of the air being blown across the arm to make it happen. That shouldn't be too bad. So 88B, let's go the right side, and let's see exactly how this whole thing would work out here. So I want to get this thing to go up to an equal level. If it's at an equal level, then a lot can be said. So you can say rho A G Y1 plus 1/2 rho A scenario A here, I guess they're saying. One side, call one side A, call the other side B. So what's going on here, guys? Well, Y1 and Y2 are the same height, so they're gonna cancel. They're canceling. because they're the same height. So when I had the same thing on each side. This guy, there's no air being allowed to blow over it. So that's 0. The other one has air blowing over it. There's going to have to be some kind of a pressure difference between the two to account for this to be the case. So they are essentially just saying, guys, at the end of the day here, P1 Is that visible, Christian? Visible, okay. All right. Again, this what's on my fingernails kind of messing things up a little bit. Try to help it out a little bit. You got here, you got just P2. Everybody else went out of there, so you got P2 right here. And do subtract P1 on each side. P2 minus P1, the pressure difference that's being created to make it happen, the density over there, well, the density over there, P1, is all just water, the A scenario. So it's looking like that. So there's a lot can be said, and that's, so let me see here exactly where you want to go with that. We're looking at this. Give me a second, guys. Another way you could have looked at it, in a sense, is there's another equation that's going to make that work as well. So let me write down a couple of them. They're saying P1 plus rho W GL. So let's see what we're trying to say here. If it's going to be brought to that point, they're essentially saying here, guys, there's a way out. This is height L also, and it's all just water. That's height L. This is all oil. And then from there, let's make it work, because everybody else is balanced out. These waters are balanced out. So the trick here is, if this guy's water, height L, and this guy's oil at height L, let's ignore these guys because they're all balanced out anyway in terms of the weight. Weight over here equals weight over there. It's not going to be an issue. So the pressures are going to have to work out that way. If that's the case, the pressure that is experienced on that side plus rho WGL equals the pressure experienced on the other side plus rho O GL. I don't like it. let me write it again. I do not want to wear this, guys. My finger's bleeding. I'm not going to trash their board and trash me also. Let me see what I can do. P1 plus rho W GL and then P2 plus rho O GL. Okay, sounds good to me. Kick that around a little bit and you end up getting, subtract P1 on each side. subtract P1 on each side, and you got this. And then subtract rho O GL on each side, and you got rho W, rho O GL. And that's pretty important. You get to here, and you get to here. What's going on here? P2 minus P1 is the same as P2 minus P1, and this guy right here is the same as this guy right here. That's pretty important. That's pretty important. So when we get it to there, we can set that stuff equal and kind of like figure it out at that point. So we got a lot of the data right here, guys. Okay, I mean, that's the claim being made. That's, we're saying that P2 minus P1 is 1/2 rho A. That's on the A side, the left side. And the other one is P2 minus P1 is equal to rho W minus rho oil GL. Great. That and that are equal, be my guess. 1/2 Yeah, let's go like that. That's going to solve it. I mean, it's not going to go bad. It's not going to go too bad at all. Rho, not the A side. A means air. Forgive me, guys. This is regarding to what air could do, where the height of the air was and everything else, and where the height of. Now, these two guys did cancel out. I mean, regarding what was happening over here, because the two things were at the same height. We're going to keep them at the same height. But rho sub A was rho air. So the A side would be the air side. The A side would be the air side. Let's go. I mean, let's figure out what it would be. B1 squared multiplied by 2 divide by the rho of air. Yeah, looks pretty good to me. That's that. Put them all in there. This is 1,000, this is 750, this is 1.29. So this is rho W. I'm sorry, the P's and rho's look alike, guys. They're all rho's right now. Rho W is 1,000, rho oil is 750, rho air is 1.29, G is 9.8, L is, see what we had actually said. I think we actually solved, we eventually did solve for it. They told us the column was 5 centimeters long, so the L would be 0.05. Grind all that out, get whatever you get here, square root it. It'd have to be 13. It'd have to be 13.8 meters per second. Definitely the problem from hell. But it's not too bad, but it's not too good either. I mean, it's very, very insightful, right? That's the argument. That's how you're doing this stuff. So I wanted to walk you through it. I mean, it took long enough that I think this is the kind of thing we want to be looking at. Topic 10 is going to be problems 38 and 48 if I can. I'm going to figure out some strategy to get us through these, at least walk you through. I want to at least, because you do have this on Canvas. So, I want you looking at it on Canvas, obviously. I just gave you a heads up that these are going to play a big role in what you're doing to finish this course. I figured I tried to pick problems that would have the biggest impact on you because I can't do all of the problems. As far as I'm concerned, all of the problems that I selected are really good problems. Not because I selected them, but because they're really good problems and I happen to find them. There's other really good problems too that I just didn't have time to do. All of the problems that I have given you are all great problems to look at as far as I'm concerned. How much time do we have? Not a whole lot. So I kind of said, okay, to finish the semester, look at these in addition to a whole bunch of other stuff. So there you are. Let me see how much. I don't know if I can do these verbatim, but I can try to give you some insight on each one of these on how to talk through it before we do cut this thing off. Okay. Topic 10 is problems 38 and 48.